So why do I care about multicollinearity to begin with? Let's write our example model down, and I'm going to make up some numbers. Let's say our model is a model of fares, and let's say our intercept is 3. We'll keep this simple. And to that 3, we'll add 2 times distance, whatever the distance of that ride is. And to that, we'll add 0.5 times duration of the ride. And in addition, we'll have a 1 times credit. So if I wanted to make a prediction, I would need a value of the distance of the ride, a value of the duration of the ride, and a value of whether the person taking the ride paid in cash or credit. So maybe I have a ride that is 3 miles, it takes 10 minutes, and the person pays in credit. And then I plug in those numbers, multiply by the coefficients, add it up, and have a prediction of fares. That would be the standard way to use this model. But we've discovered that there is multicollinearity between distance and duration. The correlation of distance and duration, as we've discovered, is around 0.63. So that's a moderately strong correlation between those two things. Okay? Now, what is the effect on the model? The effect is only in the interpretation. So it's what I get out of the model. It doesn't affect my predictions. It doesn't affect the estimation of the model. It exclusively affects my interpretation. So ordinarily, if I want to understand the coefficient in front of distance, I would say, let's assume everything else stays constant, but I'm going to increase the distance of this ride by 1. When I increase the distance from 2 miles to 3 miles, or from 9 miles to 10 miles, I'm just adding 1 mile to the ride, and I multiply that change by that coefficient to understand how it's affecting fare on average. So if I increase by 1 mile, 1 times 2 is 2, I would expect the fare to increase by $2 on average. If I increase from 9 miles to 10 miles, I would expect to pay $2 more on average. Doesn't mean that every ride where that happens is going to cost exactly $2 more. It just means on average the change was $2. I could then go on to interpret this half. For every additional minute in the car, I'm going to expect the ride to cost 50 cents more on average. So that's how I would interpret these coefficients in a typical situation. However, when I have multicollinearity, it means that these two things tend to move together. And the word tend is my problem. I don't know exactly that they move together. I don't know by how much they move when they move together. So if I try to isolate distance to interpret its coefficient, I could say the distance goes up by 1 mile, so that's going to add $2. But wait, the distance goes up by a mile, the duration is likely to go up too. So instead of being able to add $2 to my prediction because of this coefficient, I have some unknown change in the duration. Distance goes up by 1 mile, duration is likely to go up, but by some amount that I don't know. And its change multiplied by the 0.5 will also be a change added to the fare on average. So the fact that these two things are related is like I'm trying to turn one dial. I'm changing it to turn it up or down. But when I turn one dial, I'm turning more than one dial. So I can no longer isolate this influence. This influence and this influence are tied together, and I can't know by how much I am changing my prediction in fares. This is the only way the model is affected by multicollinearity. Because credit is binary and it doesn't illustrate any multicollinearity with the other variables, we can still interpret its coefficient directly. We can say that if a person pays in credit, on average, we expect their ride to be $1 more. But we can no longer interpret the coefficients of either of these directly because they have multicollinearity. In the model we just discussed, the correlation between distance and duration was 0.63. If if you can imagine this visually, what you have is two overlapping circles. You have distance and duration, and the circles are drawn to represent how much of the variation in fares they explain. You can see that they do have some overlap. That's what the correlation of 0.63 means. They are highly related in terms of their variability. When distance goes up, duration is also likely to increase. But if you had a situation where the correlation between distance and duration was 0.9, let's say, then what you have in the diagram now is a situation maybe more like this, where it's harder to see what the differences are. So let's say this is distance and this is duration over here. Now that their correlation is higher, they overlap a lot more. They're contributing more of the same things to the model, and they really don't contribute that much that's unique. So as the correlation between two variables gets higher, it might be time to start thinking about removing one of those two variables because it's redundant. Now, in the case of having 3 or 4 or 5 variables that have some multicollinearity, it might be hard to identify which ones to remove. Soon we'll be talking about variable selection techniques, and that will be a method by which we can decide which variables are redundant and which ones are really contributing something meaningful to the model.
So let's quickly summarize what to do about multicollinearity. First, we cannot interpret the coefficients of any variables that are affected by multicollinearity. We can't interpret them directly anymore. And second, we need to consider eliminating any redundant variables if multicollinearity gets too large, as it gets closer to 1 or -1.